This is a quick fire challenge. So it's one of those situations you might get a problem like this on an interview situation. People are going to not care about whether you got the right answer or wrong answer, but how you thought about the problem. And I'm hoping that you would think about dynamic programming as a solution to this problem. So the idea is, think about, again, the very last step that you did. Right before you got to Barney Greengrass, you were either at this intersection or that intersection. Of course, the other constraint here is that you have to move only up and to the left, okay? Because, of course, if you can go in circles, then you can just sit over here in the Lower East Side and eat donuts and pickles and all sorts of other great things, never leave it. So, of course, you have to move only up and to the left. That makes the problem well-defined. And so that means that right before you got to Barney Greengrass, you had to be either at this intersection or that intersection. So in other words, if we say the number of ways to get to this spot right here, okay, number of ways to get to I comma j. So the number of ways to get to that spot are simply going to be the number of ways to get to the spot that's right to the left of you, okay, plus the number of ways to get to the spot right below you. Good. So many of you got that equation right. So that means we just need to figure out the number of ways to get here. We need to figure out the number of ways to get here and the number of ways to get here. And in order to get the number of ways here, we got to figure out the number of ways to get here or here, right? So that suggests that what you should consider are the diagonals, right? You want to solve this problem like the diagonals, like we did with matrix chain. And of course, the first diagonal that you're going to end up with is Kosars-Bialy's. So if we think about it, the number of ways to get right here is just going to be 1. Okay, and again, these side conditions are also going to be like when there's nothing to the left of you, it's 0. If there's, you can never move off to the, if you're going to fall into the Hudson River or something like that, it's not something we want you to do. So we're always going to say that the number of ways to get anywhere along 2nd Avenue is there's only one way. And similarly, the only way to get past whatever this street is going to Grand or whatever, is only going to be 1. Now, at this spot, now we can start the dynamic programming solution. We say the number of ways to get right here is the number of ways to get from here to here. That's going to be 2. And right here, now that we have these two values, we can solve for this value, and this value, and this value, and this value. And now that we've had these two values, we can solve here. There are 3 ways to get right here, 6 ways to get to right over here, 10, 15, 21, okay? And similarly, 4 ways to get here, 10 ways to get right over here on, what is that, 42nd Street? No, 60s. Okay. Similarly here, there's 5, and right here to get to Time Warner Center, there are 15 ways. And you can fill the rest of this chart out yourself. So right here is 15, 36, etc. So I'll leave the rest of it for you to fill out. Notice this algorithm will handle situations like Central Park, obstructions and so forth that you can't. Do you have a question? It depends on how you, yes, it depends on how you, yeah, if I want to create this as 0, 0, then sure. Depends on how you do your indexing. In this situation, I was making this 0, 0 and increasing streets, like in New York. It's like 1st Avenue, 2nd Avenue, 3rd Avenue, etc. But you're right. If you want to index it 0 from here, then it'd be like that. So, did everybody question? So if this was 1834, before Central Park was around, you're suggesting there might be a simpler way to solve this problem? Yes, exactly. This is the recurrence right here. The solution to these type of problems all lie in that recurrence. There's only 2 ways to get to this spot. You can either come from the left or come from the bottom. And so that means at any spot, the number of ways to get to that spot, you just need to know to the left and to the below. That's a good question. Certainly, you can move this into certain spots that will reduce the number. But that's a good question. I'd have to think about it some more. What I thought you were going to say is that if there was no Central Park, there's actually a simpler way to solve this problem. You know that you have to move 6 spots this way. 1, 2, 3, 4, 5, 6. And you have to move 1, 2, 3, 4, 5 spots this way. So in any way that you're going to get from Kosar's Bialis to Barney Greengrass, you're going to have to make 11 moves, 6 of which are left. So how many ways, if I have to make 11 moves, 6 of which have to be left, how many ways are there to do that? 11 choose 6, right? That's if there was no green. This is if there was no, if Central Park wasn't there. Okay? So what I'm saying is, of course, there are some mathematical solutions to these type of problems. You can put that hat on and solve it combinatorially, or you can put your computer science dynamic programming hat on and solve it using a recurrence like this that handles general situations. We're going to come back and see this exact algorithm when we talk about shortest paths. Question? Indeed, you can use this approach and figure out how many routes are constricted by this park and subtract. We can do that as well, but I want to talk about... Let's get back to the problems that we talked about on Thursday. Just one more remark. There are 2 other handouts. There's a solution set to homework 2, and there is a handout for today's class about typesetting. Today's class is going to be 2 problems, typesetting and seam carving. Both are amazing, great algorithms that are used quite often and have remarkable results. So the typesetting problem, as I described, question, a test in this class? Someone was telling you? This test, this so-called test, is actually just another homework that is going to be called a take-home midterm. It'll be handed out October 17th. You'll have a few days to solve it, and then you'll submit them, and we'll grade them. Okay, typesetting. Remember from last class. Okay, typesetting. The situation is we have a bunch of words. We need to fit them into some margin. And the rules of typesetting, you could, of course, have white space like this, and you can have overage like that. The rules of typesetting are do not typeset in the margin, do not typeset in the margin, typeset every word, minimize the slack, right? This is the slack. And we're actually going to minimize the slack squared. And we're going to typeset 1 paragraph at a time. We realize that the greedy strategy fails if you just attempt to optimize the typesetting on a line-by-line basis starting at the first line. You'll end up in a situation like this with a penalty score of 197, whereas if you solve it with a dynamic programming approach, you can get a smaller penalty. To frame this as a problem, we say the input consists of a series of words and a margin, and the output is going to be the line breaks. And as I mentioned, the way to specify line breaks are simply to give indices. The first line consists of the first L1 lines. Line 2 ends at L2. The last line, of course, ends with the last word, but begins with the LX plus 1 line, a word. Okay? And the constraints that we need to satisfy informally, we need to make sure that no line exceeds margin. Okay? So we need to have Ci is less than M, where this is basically the characters on line I. And then we also want to minimize the slack. And the slack is basically this extra space squared. Minimize the sum of the slack on each line squared. This is the more formal way of writing this formula. Now, how did we solve this problem? From last class, we took this dynamic programming approach. We said, let us first define a variable that will represent our solution. The best n is the smallest penalty for which the first n words can be typeset. In other words, what's the best way to typeset the first n words? Our goal is, of course, to come up with a dynamic programming equation for best n. Once we have that equation, an algorithm will fall out. How did we come to this solution/equation? As with many of these dynamic programming problems, we imagine the very last step. We said, what happens in the very last step in the optimal solution? So in the optimal solution, one will have a series of words here placed. And there may be some little white space right here. One will come to the very last line and observe two things about the very last line. First, the first word of the last line. We can express our best solution in terms of this wall, right? Because depending on which word is the first word of the last line, that's going to define the slack for the last line. So depending on whichever word is the first word of the last line, that's going to determine what the slack for that last line is going to be. And now we have a way of expressing what the optimal solution is going to be. The optimal way of typesetting n words is going to be the best way of typesetting the first fwall minus 1 words plus, so the best way to typeset the first n words is going to be the best way to typeset the first fwall minus 1 words plus the slack squared that's going to result when you start the last line with this word, fwall. Question? Well, remember what we're doing right now is saying, let's think about the optimal solution. The optimal solution does have, some word has to be the fwall. So whatever word that is, it's going to be one of the n words that we start with. Whatever that one word is, has to satisfy this equation. In other words, this is the structure of this problem. The best way to typeset n words is going to be the best way to typeset some n minus k words, and then the slack for that last line. Question? Yes. So in real-life typesetting, what you want to do is avoid what you call an orphan, like a last line with a single word. Typically, you'll mess around with the other situations in order to eliminate those. In this situation, in the simplest case here, let's keep it simple, and let's just minimize the slack that I described. Our solution, we are attempting to minimize this term right here, which does not take into account the fact that you might have a widow or not. All right. So here's the picture right here. Okay. So if the first word of the last line is WL, let's define a variable slack ln, which is the slack when the line starts with WN and goes to word n. Right? So this right here is word n. So as I wrote on the previous slide here, this is just a clearer version. In fact, I think I have it right there. The best of n is going to be the best of L minus 1 words plus the slack that we get when we start the last line at word L. How many candidates are there for the fwall? If I have n words to typeset, what are the possible words that could be the first word of the last line? The first word could be the first word of the last line. The second word could be the first word of the last line. The third word could be the first word of the last line. So there are n candidates, and that means we can identify the fwall. Because now all we have to do is say that best n is going to be the min So here we go. Here's our algorithm. Best way to typeset n is going to be the min of the best way to typeset the first k words plus the slack squared when you begin typesetting the slack squared when you typeset a line that begins with word k plus 1 and ends with word n. Let me illustrate it this way. So let us ask the question, is the first word of the last line? if we attempted to typeset, if the first word, if W1 was the first word of the last line, that means that there's only one line, which means the entire paragraph has to be typeset on one line. And conceivably, in this situation, slack is negative. In fact, the set of words go over this margin. We can handle this situation by just defining since the first rule of typesetting is you can't go over the margin, whenever a slack goes over the margin, we'll define that term to be infinity. So let me start from this equation, right? So again, best way to typeset n words is going to be the minimum of the best way of typesetting 0 words plus the slack of 1 to n squared. Or the best way of typesetting 1 word and starting the last line with words 2 through n. At some point, we're actually going to come to the situation which is the actual optimal solution, where Wj does happen to be the first word of the last line in the optimal solution, and one of those lines right here is going to be this one. Best j plus s of j plus 1, comma, n squared. Question? Yes. So the question is, why is it best to minimize? Why is our target, why is our goal here, or let me express it on this slide right here. Why is our goal to minimize this quantity instead of something else? That's a legitimate question. And perhaps someone with more aesthetic sense has a better function to describe what is the best typesetting. But for this problem, the simplest case of typesetting is just to minimize this slack squared. So I'm answering you, yes, in real life, perhaps there are other considerations that we want when we typeset a book. And we can add those constraints in by modifying this function and making this function more complicated. But for this exercise, we're trying to learn about dynamic programming and how dynamic programming can solve this problem. And so I want to stick with the simplest function which describes an optimal solution, which is that. Is that a reasonable answer? All of your concerns are essentially captured in this line right here. You're also considering the best situation of typesetting the... So you might be... What you're saying is, perhaps the best idea is to minimize the space on the last line, figure out what that would be, and then go to the line above and minimize the space on that line. That would be a greedy heuristic, which just like in our class, when I did it the other way, when I started by minimizing the front line, the first line, it wasn't optimal, right? So similarly, a greedy heuristic is not going to work for this problem, but we're not doing something greedy. We're looking at the best, all of the previous n solutions, and then adding the slack that would result from those solutions, and considering which of those is the best. So I'm going to wait for some questions about this. Does everybody understand why the problem is completely expressed by this equation? There are only two things left. Did you understand how I set the problem up and came to this equation? Once you get to that point, the next question is, how do we implement that? And that's the second aspect of dynamic programming. What order are we going to take? And in this case, the new aspect of the dynamic programming is that we had this extra variable. Our previous examples of log cutter and matrix chain multiplication, they didn't have these extra variables. They were just 1D example of dynamic programming, a 2D example of dynamic programming, and now we're talking about a 1D example of dynamic programming with an auxiliary variable that we have to compute. Questions about the setup? The best way to typeset 0 words is going to cost you... The best way to typeset 0 words on... I guess we can just define best 0 as 0. I've worked out an example, and I hope that going through that example will clarify some of this as well. But this is the conceptual aspect of this problem. How did we get here? We thought about the optimal solution. The optimal solution has some word that begins the very last line. that word has to satisfy the property that the total solution is going to be the best way to typeset this many words plus the slack that was induced by starting the last line with this word. So this is going to suggest an immediate algorithm for this. Because once we have this equation right here, all we got to do is make a table for these slack variables and then run through a loop like this. For i's 1 to n, best of I is just going to be the min, as j goes from 1 to I, of typesetting the first j words and then considering the slack that was induced by starting the last line at j plus 1. So, as I mentioned in last class, I've posted a C program that does exactly this. It's just these 6 lines of code. You initialize an array, and you start this for loop right here, and then this is right here corresponds to this minimum condition. In other words, translating this equation into an algorithm, an exercise I think all of you should do to make sure you understand this technique, is relatively painless. It's like this. The unspecified step in this algorithm is this first one. How do you make a table for this slack? Remember, slack ij, it's going to represent the slack that results when you start a line at word I, you end a line at word j, and that's going to create some slack right here. So, the simplest case, when you start a word at start with word 1 and you typeset only word 1 on that line, what would the slack be? What is this yellow bar right here? If this was the margin m, remember that's a parameter of the problem, yes? Exactly. Slack 1,1 is just the margin minus the length of the first word. What happens when you typeset the first 2 words? What is slack of 1, 2? Yes? It's the slack, it's this slack right here, but when you added the second word, you first added a space right here, okay? And then you added W2. So it's going to be the slack that you had 1,1 minus 1 for the space minus the length of the second word. So we are going to use dynamic programming again to compute these slack variables. So here we go. Slack I, j is going to be m minus wi if I is equal to j. And otherwise, it's going to be slack of I, j minus 1, minus 1 minus the length of that jth word. So here is a loop that will compute exactly this function. We start right here by just doing m minus w1. And then this value is just going to be s11 minus 1 minus the length of w2. This one right here is just going to be that one minus 1 minus the length of w3, etc. We're going to go through an example in just a second. In fact, let's get to it. So, let's start with our favorite sentence of a novel. And what I've done here is I've just represented each of these words. I've just taken the length of each of these words. It doesn't exactly, this algorithm doesn't really take into consideration ligatures and what the characters are. All it's going to do is care about how long these words are. So let's represent that input just as this array of numbers. Now, if you get your handout, the first step of the algorithm was to make the Sij table. So let's take the problem when it starts with m is equal to 42. And now S11. So this is this table right here is Sij. S11 is just going to be m minus the length of that first word, which is 2. Does everybody understand this array of numbers right here? This is the length of the ith word. So that means S11 there is going to be 42 minus 2, which means it's going to be 40. And S12 is going to be 40 minus 1 minus the length of the second word. So it's going to be 36. Now spend the next 2 minutes filling out this table with your neighbor. And in fact, I'm going to try to, yeah. You can discuss it. Question. Okay, let's regroup. I want to make 2 points clear. First, this step right here is the first step of the algorithm. It's kind of like a pre-computation. We need to solve this step before we can actually do the typesetting, which is the other 2 lines in that algorithm. Now, I think most of you got the first row right here. A few people asked, how do we start the second row? Well, this equation defines it. The second row right there, S22, it reflects the slack when typesetting word 2 up to word 2 on a line. And so that slack is going to be m minus wi. So the second word has length 3, so this is going to be 42 minus 3, or 39. Question? Would this array be n by n? Yeah. Yes. So look at the code the code right here that reflects how this algorithm would work. You just allocate an n by n array and fill it in this diagonal way. So here's what that first row should be, 40, 36. In fact, here's what the first 2 rows should be. In fact, if you turn it around, I believe the answer is right there, right? Okay. So the first step of the algorithm was to make that table. Good. Now the second step of the algorithm, once we have that table, is to fill out the best array just like we did on those 2 lines right here on this third screen. These 2 algorithms in this chunk of code right there. So best 0 is 0. Best 1 is going to be either, best 1 is essentially going to be best 0 plus s of 1 comma 1 squared. And so that's going to be 0 plus 40 squared, or 1600. Right? So what this says is, if you had one word to typeset, it was the best of times. So if you just had to typeset it, the penalty would be 1600. That's the best way to do it. Best 2 is going to be a minimum. It's either going to be best 0 plus s of 1, 2 squared, or it's going to be best of 1 plus s of 2, 2 squared. Okay? Now that top line is going to be 0 plus, let's look at s of 1, 2. That's 36. Okay? And that's going to be 1296. Or this bottom line is going to be best 1, which we've already computed, 1600 plus s of 2, 2 squared, 39 squared. Okay? And that is going to be a large number, because we already have 1600 in. So that means best 2 is 1296. Spend a minute with your partner computing best 3. First of all, best 3 is going to be the minimum of 3 numbers. What are those 3 numbers? Spend 2 minutes computing those 3 numbers, please. And then tell them to me. All right. So I hope you came to the conclusion. You had three choices here. These three choices, they basically reflect typesetting as it was the. That's what that line corresponds to. This one corresponds to typesetting the first word, it, and then having was the on the second line. And this third line corresponds to having it was the as two different lines. And of course, the best way to do that is this right here, which corresponds to 1024. The code is posted. You can run these examples yourself, and you can fill out the rest of this to make sure you understand this algorithm. 2 questions. Go for it. The first number of the second line? So that number is S22. This number right here is S2, 2. And that, if you look at the equation, S of I, is just the margin minus the length of that word. And since the second word is, this corresponds to it was the best of, so it was is 3 characters. So this is why this line is going to be a 39. Okay, S22 is equal to margin minus 3, which is equal to 39. Similarly, this one, S33, is also going to be M minus 3, which is 39. Did that clarify it? What does it stand for? S22 stands for the slack if you, when typesetting word 2 all the way up to word 2. So in other words, S22 is just, if I was going to typeset the second word on its own line with nothing else, was. The second word is was, so the slack would be 39 characters. The margin is 42, the second word is was, the slack would be 39. Right? Sij is going to be the slack of typesetting the second word to the ith word to the jth word on one line. Does that make sense? Highlights. We've upped our game here with dynamic programming. We've taken something slightly more complicated than a 1 or 2 or 3-dimensional DP. We've added this other variable, this slack variable, which helps us solve the original problem. Everybody understand that? Good? I want to at least end today with what I think is one of the best examples. By the way, the running time of this algorithm, how do we analyze it? How much to make that table? I'm giving you an algorithm. There's no guessing involved here. How much to make that table? Great. And then how much to do this loop? Right? This takes n iterations. And this minimum right here is going to involve n iterations as well. So that's an n-squared algorithm. The whole algorithm is n squared. So this is why typesetting, like LaTeX, the typesetting algorithm is squared in the number of words in a paragraph. Typically, there are not that many words in a paragraph, maybe 200, 300. And of course, there are ways to speed this up. But it's still roughly, it's not an efficient algorithm like n log n for sorting. So the next dynamic problem, the next DP problem I want to introduce is this problem called seam carving. The best introduction to this is this video. Let me see if I can get it up.
Digital media today has the ability to support dynamic page layouts. By changing the window or display size, we can change the layout of a document. However, images embedded in a document typically remain rigid in size and shape. Resizing is also important to fit images into different displays. Current techniques, including cropping or scaling, are limited in their abilities to capture the image content. We present a method for content-aware resizing of images. Our technique enables resizing while adapting the image content and layout. This is sometimes called retargeting. We also define a flexible multi-size representation for images.
So do you understand the problem? You have some image, but you want to show it on a smaller aspect ratio display. You can either crop it, which removes parts of the image, or you can scale it, which distorts the image. This is a third way of doing it.
Images that supports continuous resizing. An image can be shrunk in a non-uniform manner while preserving its features, but it can also be extended beyond its original size. Instead of scrolling through images that do not fit in a given display, we gracefully resize them to fit inside the window.
Oh my gosh!
For example, assume that we need to change the width of an image. The simplest way to do this is to remove columns of pixels from the image. The best column to remove would be the least noticeable or least important column. We can search for this column by defining an importance or energy function on the image. In this example, we use the gradient magnitude of the image. Next, we look for the column which contains the least energy and remove it. However, using such an approach quickly leads to serious artifacts. Therefore, instead of using rigid columns, we search for connected paths of pixels, or seams, from one side of the image to the other that contain the least energy. This can be done using a simple dynamic programming algorithm as described in the program in both vertical and horizontal directions. Here's another example of an image, its energy function, and the least noticeable horizontal and vertical seams. By successively removing horizontal and vertical seams, the image can be resized in a non-uniform manner. The order of seam removal in an image defines an order on the pixels of the image. By storing the simple indexing information, we create content-aware multi-size images. In this image, we color all pixels according to the order of their seam removal from blue to red. To enlarge an image, we first calculate seams as if we were to shrink the image. Instead of removing these seams, we insert new seams in these locations. The pixels of the new seams are the average of the pixels alongside the new seam positions.
What?
This enables a smooth transition between reducing and enlarging the image size in multi-size images. We have tested different possible energy functions for retargeting, such as entropy, saliency, histogram of gradient direction, and eye movement measurements. The results depend on the given image, but simple gradient magnitude often gives satisfactory results. For certain content, such as faces, where the relations between features are important, we define a simple user interface enabling the designer to protect these image areas. The application is also used as an authoring tool for creating multi-sized images. Note that in this specific example, automatic face detection can be used to identify the areas that need protection. To illustrate another application for this tool, we show a simple object removal procedure. By adding negative weights to the energy of an image, the user can attract the seams to pass through specific areas first. By reducing the size of the image, these areas are removed first, in effect erasing them. To retain its original size, the image is enlarged by using seam insertion. Note that this technique changes the whole image and does not simply erase the objects marked.
You erase it and then you re-expand it without that person.
More examples can be found in the paper and the supplemental materials. Thank you for your attention.
All right, that's me right there. And okay, watch a live demo of this. We can do you see the seams? So the algorithm works. People have implemented it. You can try it yourself. How does it work? Dynamic programming. The gist of it is, we need to find the lowest energy scene, i.e. the lowest energy path from the bottom of this image to the top of the image if we're trying to make it shrink horizontally. We're going to use dynamic programming in order to find that path, that lowest energy path. We'll talk about that on Thursday.